Hello students, this is Mike here. I'm trying to provide instructions in the form of this video tutorial for the last two labs of our biochemistry lab course. Before doing so, I have to acknowledge Dr. Doug Harris, who's created these labs and who gave me the personal one-on-one training that I needed to be able to produce this video. The first of these two labs is entitled Inhibiting the Flu, and will be worked out on a software program called Discovery Viewer Pro. I'll go and show you how this is done. In our computer labs here in our USU building, I've had installed on multiple computers a copy of this software program right here, which once again is called Discovery Viewer Pro. Go ahead and click on it to open it. It will of course bring up this error box, to which you can just hit OK and ignore. Once you're at the welcome screen, I would like you to begin by drawing 6 water molecules. What you do is you reach over here and grab this pencil tool, and you'll go ahead and draw one dot. Now, once you draw a dot, if you keep your pencil tool here on the canvas, it will want to create a second dot, a bond to that first atom. If you don't want to do that, which we don't in this case, move your pencil tool off of the canvas and then back on. You can now draw a second dot. Now I'll continue doing that until we put 6 total dots, because I want to make 6 molecules of water. And I would like you to make them any way you like, but very close to each other. At this point, we now want to see our hydrogen atoms, so we're going to hit the select tool and select out here so that it deselects all of these atoms. Otherwise, if you click on one of them and it's yellow and highlighted, it's now selected. We want to deselect all of them. Now I'll click this H button right here. It shows all of the hydrogen atoms. It's a little bit congested, so if you click this black square here, it will zoom in a little bit. You'll notice that these molecules each have 4 hydrogen atoms around the center. The reason is because the center at this point is carbon. If you click each molecule right here and then type the letter O on your keyboard, it will convert it into oxygen directly. We'll go ahead and do that for all these molecules right here. For some of the molecules like this one here, it's kind of difficult to get into it. So if you reach over here and grab the rotation tool, you can rotate all of the molecules so that you can see that carbon atom a little bit more clearly. I go back to the select tool, click the atom, type the letter O. Now all of these should be water molecules, and indeed they are. Now what we want to do is energy minimize these. In other words, we want to determine what the lowest energy and most stable arrangement of these 6 water molecules is going to be. The way we do that is by first determining what is the major intermolecular force that these molecules are going to have. So I'm asking you, what is it? What major intermolecular force do water molecules have? Of course, you know the answer is hydrogen bonding. So we'll go up here to Tools and then select Monitors and select Hydrogen Bond. You'll notice that it shows a dashed line connecting each of the hydrogen bonds here. Once again, it is very congested and very unlikely that water molecules would in real life maintain this relative three-dimensional configuration with each other. So let's go ahead and minimize that and see if we can move these water molecules around until they do get to that magical place. We'll go over here to Modify, Drying Minimize. Here we'll make a couple of parameter changes. We want to do 1,000 iterations. We want to have our convergence criterion be 0.01. We want to make sure that all 3 of these boxes are checked, and we would like to do 1 step here. Then we'll go ahead and hit OK. It will now begin to move these water molecules around until they've achieved the lowest energy or more stable configuration or conformation that they can relative to each other. We're now done. If you want, you can use the rotation tool to look and see that all these molecules should be kind of in a nice, happy place. We'd now like to take a similar approach, but with a different molecule. This one will be cyclohexane. So what I'd like you to do is open a new window by clicking this new icon right here. And here on this canvas, we're going to draw cyclohexane. We can do that pretty quickly by selecting this tool right here that has a 6-membered ring, and then clicking one time out here in the canvas. If you want to see the hydrogens, you can click this H button right here. Try clicking the rotation tool right here and then rotating the molecule around so that you can make sure that it is indeed cyclohexane. Yes, we can see there are CH2s all the way around the ring. Does this cyclohexane look like it's in the most stable conformation? If we rotate further, you can stare down the plane of it. That does not really look like the traditional 6-membered chair conformation that we are accustomed to learning about in organic chemistry, does it? That probably means that this is not in its most stable conformation. So let's go ahead and run a Drying minimization. We'll go here to Modify, Drying Minimize, and keep the same parameters. If we hit OK, the atoms should rearrange and hopefully find a more stable conformation. I'm going to deselect the hydrogen so that I can see it more clearly. By selecting the rotation tool, looking at it more closely, I can see that, yeah, it actually does look like a 6-membered chair conformation, kind of like we're accustomed to in our organic chemistry courses. Now, I should warn you that occasionally when you do a Dryden minimization of cyclohexane, it doesn't really look like it's at a chair conformation. How in the world can that be? Well, the reason is because the program is set to move the atoms around until they achieve some type of local energy minimum. Sometimes, unfortunately, that local energy minimum is not necessarily the correct conformation. Let's go ahead and see if we can look at the actual energy level of this local Dryden minimized cyclohexane that is obviously not a chair conformation. Staring right down it, I can see that it's completely planar and not a chair. That becomes more clear if we remove the hydrogens here. Click on Window, New Data Table. If we stare up here, it says initial Dryden energy. That was the energy level that the cyclohexane was at the very beginning. And then the final Dryden energy is the energy level of the conformation now after making the minimization adjustments. Let's go ahead and minimize this window by clicking the minimization, and then we'll maximize our ring again. We want it to be a chair conformation, which sometimes it ends up doing by itself nicely and sometimes it doesn't. Let's go ahead and click the selection tool and grab one of these atoms and then stretch it way out here. You'll notice this is very, very unchair-like. However, this will tell the software that we want to make the shape look a little bit more like that and see if we can get to an even lower and more stable energy level. We have to, of course, make sure that we deselect everything. We go to Modify, Dryden Minimize, and then I'll select 1,000 iterations. Hit OK, and it starts doing its magic. It's now done. We look at it closely. You can see once again that this is a nice chair configuration. We can also see the hydrogens if we want to by clicking the H button here. Let's go back up to the window and we'll click on New Data Table. You can see that the final Dryden energy of this conformation is much lower than it was before, which indeed lends credence to the idea that a chair conformation is much more stable than a planar conformation for a cyclohexane ring. What's the point of all of this? The point is that you guys should understand this computer modeling software has its limitations. In other words, you have to use your conceptual knowledge of chemistry, such as the fact that a chair conformation of cyclohexane is more stable than a completely planar conformation, in order to help guide you, and don't just take every single number that the computer spits out at face value. In effect, theoretical chemistry, which is the field of chemistry that specializes in the art of calculating the behavior of molecules on a computer, has to be coupled with actual theoretical knowledge. In other words, computers are not infallible.